First, I will start with the structure essay part. Okay, shall we read the first one? First structure question. The diagram shows the motion of a long jump athlete during the run-up and the jump. From point A to point B, the athlete runs along the straight track with uniform acceleration of 2 meters per square second. From B onwards, the athlete leaves the ground and performs a jump. Okay, so already we have read it. So we know what's going on there. Now, athlete is running on a horizontal track and then he jumps. That's what happened. So let's draw the image first. So this is the horizontal track that he runs. Then he has to jump from here. Okay, I'll draw him. This is the point A. At point A, she starts with the 0 velocity. Then she's running. Okay, and after a 4 meter distance, she comes to point B, where she makes her jump. Okay, from point B, she's in a projectile motion, as they say, and she will come to the same horizontal level or the ground at point C. She will come to the ground at point C. Okay, so this is what happening. Now, I will answer these questions one by one. Okay, first, wait, let's mark it. Here, to run this first 4 meter distance, she has a acceleration of 2 meters per square second. Okay, let's see what happens. Part A, Roman number 1, determine the time taken by the athlete to travel from point A to B. Okay, so she is moving in a horizontal line and with a constant acceleration. If she is in a constant acceleration, we can use the equations of motion. So I'm applying S equals ut plus half at square. I'll mention it here from A to from A to B. You have to mention it. I'm applying S equals ut plus half at square from A to B. Her initial velocity is 0. So ut multiplication will be 0 here, as her initial velocity is 0. Then half acceleration to t square. She has to move a 4 meter displacement. Okay, 2 will cancel out. T square is equal to 4. So her running time is equal to 2 seconds. So if t equals 0 here, it will take her 2 seconds to reach the point that she needs to jump. Okay. Then I have given 2 marks for that. I will mention the marks here. I have already uploaded the marking scheme, but I will show you the marks, how they were given. Okay. Here you are given 2 marks. 2 marks. Okay. Then determine the magnitude of the horizontal velocity of the athlete at point B. Okay. I'm applying V equals U plus AT for the horizontal motion. At the point B, let's say her horizontal velocity is VB. Okay. VB is equal to initial velocity 0, acceleration is 2, and time taken, we already know that it's 2. Okay. So she will have a horizontal velocity of 4 meters per second at this point. So horizontal velocity at the jumping instant is equal to 4 meters per second, the horizontal velocity. But there's another thing. If you read the paragraph carefully, not only this horizontal, at the jump, she will maintain this 4 meters per second velocity. It will not change due to the jump, as they say in the paragraph. Instead of this, rather than this 4 meters per second horizontal velocity, there's another velocity. At the jump, she has achieved 5 meters per second vertical velocity too. She has achieved 5 meters per second vertical velocity, and her 4 meters per second horizontal velocity also there. Both velocities are there. When you have a horizontal velocity and a new vertical velocity gain, what will happen? Due to the horizontal velocity, she will move forward. Meantime, due to the obtained vertical velocity, she will move up in the motion under gravity method and then come down. And she is moving up and coming down due to this velocity component. And she is moving forward due to this velocity component. And what will happen? She will gain projectile motion by the combination of velocities, no? Okay, so she will be in a projectile motion after that. Okay, now let's go to the projectile motion part, but let's follow the question numbers. First question, you found the velocity, no, time taken to reach this 4 meter distance, and then the velocity gain. Roman number 3, what's that? Clearly indicate on the diagram the forces acting on the athlete during the run-up. Okay, I'm going to teach it now. Wait, I need my red pen also. Wait. I'm going to teach it. Now, how to draw the forces acting on her, when she is on the run. She's in the run. When she is in the run, how to draw the forces. Okay, I will draw a person running. The first thing, her weight is there. Weight mg, it's there. That's obvious. Okay, here I have given you 1 mark for this place. Now I am giving marks to this one. Her weight is there, so you have to mark mg. And the next force, I'm going to mark the forces when she is on the run. Okay, her weight is there. The next one, when someone touches the ground, there's a normal reaction force created on her legs. When someone touches the ground, there's a normal reaction force created on her legs. R, normal reaction force. It is also there. Weight and the normal reaction force. And the next thing, now in the run, she gets an acceleration to the forward direction. So to get the acceleration to the forward direction, she need an external force towards this direction. To have acceleration, when you are running, you get acceleration towards that direction. To get that, you need a force towards that direction. So what is the force giving her this acceleration? Weight, mg and r, they are vertical forces. Vertical forces can't affect the horizontal. So this acceleration is not gained by this mg and r. So what is the force that she gets this acceleration? To get the acceleration, she needs a force in that direction. This is what happened. When someone is running, what he do? From the back leg, the person running from the back leg, what he do? He tries to push the back leg backward. When someone is running, what he does? He tries to push his back leg, the leg on the ground. He tries to push that leg in a backward direction. When he tries to push his back leg in the backward direction, what happens? From the ground, he pushed the ground in the backward direction, and there will be a Newton's third law component acting upon him to the front direction. And that is the force that will gain this acceleration. Okay, when someone tries to run, what he does? He tries to push the ground towards the backward direction from his leg. So the person creates a force to the backward direction on the ground. Then what happens? From ground, there will be a Newton's third law component acting on the man, and it will be in the opposite direction. So what is the opposite direction? It's the front direction. So there will be external force acting on the man on the front direction. This force will give the acceleration. So these are the 3 forces that you have to mark. 1 mark for mg, 1 mark for r, and the other mark for this force. And here I need to teach you something else also. What is this force? It is a friction. How it becomes a friction? I'll tell again. When someone need to run forward, he has to take his back leg and he has to try to push the ground in a backward direction. So the person applying a force on the ground in the backward direction, from Newton's third law, ground will apply a force on the person in the frontward direction. So it will be helpful for him to get this acceleration. Okay, now I said this force is a friction. Why? What we do, we try to move our leg. How we try to push the ground? We try to move our leg in a backward direction. We try to move our leg in a backward direction. That is how we try to push the ground backward in order to get the front force from the Newton's third law. So what we do? We try to push the ground backward. When we try to push the ground backward, our leg seems to be moving backward on the ground, tends to move backward on the ground. So the friction will create in the front direction. Why? When object tries to move in a certain direction, the friction is created in the opposite direction. So when we try to move our leg to the backward direction in order to push the ground backward, what will happen? It's a frictional force that's created on us in the forward direction. Why? Our leg is, we try to move our leg backward. Then opposite to that, there's a force acting from ground on our leg in the forward direction. So you have to understand that. I'll give you a small star mark here. Okay, write down a small star mark about this frictional force. Write down a small star mark. When we need to run forward, when we need to run forward, when we need to run forward, we push the ground. When we need to run forward, we push the ground backwards. When we need to run forward, we push the ground backward from our leg. When we need to run forward, we push the ground backward from our leg. So we create a force on the ground. So we create a force on the ground to the backward direction. So we create a force on the ground to the backward direction. And from Newton's third law, ground will create a, forward force on our body, giving us the front acceleration, To push the ground backward, we try to push the ground backward, we try to move our leg. To the backward direction. It's not actually moving, but imagine we are trying that. When we are running, we try to push our leg into the backward direction. It's not actually moving, but the tendency is that we try to move it backward. Okay, we try to push our leg in the backward direction. So opposite to that motion, ground will, opposite to that motion, the force created by the ground, on our leg, is a frictional force. Is a frictional force. Okay. So you have to know this theory really well. You have to know this theory. When you are marking the forces acting upon the man, normal reaction, when someone touches the ground, there's a normal reaction upward, his weight, and as he moves into the front direction with the acceleration, there should be a force acting upon him horizontally to the front direction. How he gains that? When we are running, we try to push our leg, not actually our leg is not moving backward. It's true, but we try to move our leg backward. We give it just a push like that. Okay, when we try to move our leg backward, that means we are creating a force on the ground in the backward direction, and from Newton's third law, there will be a force acting upon us to the frontward direction, giving us this acceleration. So I have to mark that. Okay, why? Vertical forces can't give the horizontal acceleration. There should be a horizontal force. That's how we gain that. Okay, and this force, for your knowledge, this force is a frictional force. Why it's a frictional force? We try to move our leg backwards. Let's say our leg is the object. We try to move it backwards. Then always the friction is opposite to that motion. So friction will be created in the front direction. So this is a frictional force. Okay, know that theory part. Then I'll come to the fourth part. Explain why the athlete must exert a force on the ground in order to increase the speed during the run-up. Okay, so I'm not going to explain the fourth part. I have given a single mark, 1 mark for that fourth part. That's the thing I explained to the star mark. So I'm not going to explain it again. Okay, I already explained. I gave 1 mark for the fourth part. Okay, then I'll come to part B. During the jump from B to C, determine the maximum vertical height during the jump. Okay, now I'm coming to the projectile motion part. From B to C, it's a projectile motion. Okay, in that projectile motion, you are asked to find the maximum height. You are asked to find H max for that projectile motion. Part B, question number 1. Applying V is equal to U square plus 2AS for max height. Okay. Initially, athlete got a 5 meters per second velocity upward as an initial upward velocity. At the maximum height, upward velocity is 0. At the maximum height, upward velocity is 0. So I'm applying the equation upward. At the maximum height, upward velocity is 0. At the beginning, she gained a velocity of 5 meters per second, 5 square, 2. When an object is moving upward, it's under motion under gravity, so acceleration is minus 10 H max. Okay, 20 H max is equal to 25, so H max is equal to 1.25 meters. The max height 1.25 meters. Okay, I gave 2 marks for that. Okay, then you are asked to find her flying time. I'm applying in the same question. In the same question, you are asked to find the flying time. Applying S equals ut plus half at square for the full motion. Okay, from here, from point B, I can say from B to C. That's nice. Not full motion. I can say from B to C. That's nice. Okay. At the point B, she's on the ground. She will move like this and come to ground again. Yes, she has a horizontal velocity after her flying time. But vertically, what has happened? She has come to the ground again. So even though she has a horizontal velocity, her vertical velocity will become 0 again when she reaches the same level, same ground level after the flying time. So when I'm applying S equals ut plus half at square in the vertical direction, after flying time, what happens? The vertical velocity, vertical displacement, it becomes 0. Yes, she has moved horizontally, but what happens with the vertical displacement, the y coordinate, it becomes 0 again. So applying S equals ut plus half at square to the y direction, y coordinate has become 0 again when she reaches the same level. Initial velocity upward is 5, flying time t. half moving up. So acceleration of gravity minus 10 t square. 5t square is equal to 5t. So her flying time is equal to a 1 second time. 1 second time. Okay, I gave 1 mark. Within that 1 second time, her horizontal velocity will not change. Her horizontal velocity will not change. Why? The acceleration of gravity is vertical, so it doesn't affect the horizontal. Vertical vectors doesn't affect the horizontal. So horizontally she doesn't have a acceleration when she is in the projectile motion. Their resistance is negligible that they have given it. Okay. So horizontally I can apply S equals ut. Horizontal velocity component will remain same for 1 second time until she reaches the ground again. So she will have a horizontal range of 4 meters due to the jump. Okay, that's what they ask here. I have given another mark to that. Now, as the final thing, you are asked to mark, you are asked to draw 2 graphs. How her horizontal velocity component change and how her vertical velocity component change during the motion. Let's draw 2 graphs. The first graph is to draw, you have to show the horizontal velocity with time. Okay, V horizontal. Can you remember? She had the acceleration first from A to B. When she is having acceleration in a velocity time graph, acceleration is represented by the gradient. She had the 2 meters per square second constant acceleration, so the graph should have a constant gradient. As it's a velocity time graph, the graph should have a constant gradient. Okay, so this is the constant gradient. From a velocity time graph, the gradient will give you the acceleration. As it's plus 2, the gradient should be plus 2. So this is the positive constant gradient graph until it becomes a 2 second time where she reaches B. When she is at A, now after 2 seconds, she reaches B with that acceleration. After that, she is in the projectile motion. Inside the projectile motion, the vertical velocity changes, but the horizontal velocity component stays same. So it will not change until the 3rd second. Why? The flying time is another 1 second time, so completely will take 3 seconds. So from 2nd to 3rd second, that means in the projectile part, her horizontal velocity component will not change. It will remain 4 with a value of 4. Okay, let's draw the vertical velocity component. Let's draw her vertical velocity component. What happens to the vertical velocity component? From A until she reaches point B. That means from t equals 0 to t equals 2. T equals 2. What happens? She is running horizontally, so there's no any vertical component. The vertical component is 0. After that, suddenly what happens? She gains a velocity component of 5 at her jumping point. So suddenly it becomes 5. After that, what happened? You have to draw the graph to indicate the velocity in a motion under gravity case. Why? Initially, she doesn't have a vertical velocity until she finished 2 seconds. She's in a horizontal motion. Then she start to jump vertical. She gets a vertical velocity of 5 meters per second due to her jumping attempt. It's 5 then. After that, what happens? She moves up until the max height. She moves up until the max height. Okay, when she is moving up, her velocity reduces, and at the highest point, what happened to the vertical velocity? It becomes 0. The velocity reduces, and this is the max height. It becomes 0. After max height, what happens? After the maximum height, again she comes toward ground, and vertical velocity component develops in the opposite direction. in the towards ground it develops. So moving up, velocity is plus. After the max height, when she is moving down, velocity is minus, and it is increasing due to the gravity. Okay, so the minus velocity increases. So this is the graph. This is the graph. Okay, so I gave 2 marks for this part and 2 marks for this part. Okay, altogether you will have 15 marks there. Altogether you will have 15 marks there. Okay, then I'm going to discuss the most important question in the paper, the second question. Okay, finish this, and I'm going to discuss this second question, the essay question. Actually, it's also a semi-essay question. As we are in the beginning, I will develop you little by little. It should be a gradual growth. Okay, it should be a gradual growth. So little by little, I will increase the heavierness of these questions and bring you to A plus, bring you to A pass with time. Okay. Now, I'm going to discuss the next question here. The second question, it's also a semi-essay one, structure one. It's about a person who is trying to move upward using a certain method. Okay. Yeah, you might have to know some theory. Wait, I'll explain. I'll explain with the theory part also. Right. Okay. Question number 2. The diagram shows a man standing inside a lift. A man is standing inside a lift or a container or a vessel or a small cage, whatever. He's inside a box, let's say. So, inside a lift, which is suspended by a light inextensible cable passing over a pulley fixed to a ceiling. Man pulls over the other end of the cable downward, and the lift starts to accelerate vertically. Okay, let's draw it. Now, here the cage is present, cage or the vessel or whatever the thing, the lift, whatever. So, the man is here. The man is here. Now, there's a cable connected to the roof of the cage, and it passes over a pulley which is suspended from the roof, and the cable comes like this. And what happens after cable is here? What happens? This man pulls the cable downward. So this is F1. What is F1? What is F1? Force acting on the cable by the man. Okay, he's inside the lift, and there's a cable connected to the top of the lift, and it's passing over a pulley. Then it comes from the other side, and this man pulls the cable downward. I marked it as F1. F1, force acting on the cable by the man. He pulls the cable downward. When he pulls the cable downward, cable will come down. So it will pass the pulley in a clockwise direction, and the cable comes down from this side. It passes the pulley from a clockwise direction, and it will make the lift move upward with the acceleration A. So that's what happening here. He pulls the cable down, and cable will pass the pulley in a clockwise direction, bringing this lift with the upward acceleration. Okay, so this is what happening. Okay, simple A. State the conditions required by the cable and the pulley to maintain the same tension through a cable. Okay, that's the theory part. To maintain the same tension throughout a cable, the cable should be a light. massless, inextensible, inextensible one. Okay, so let's write it. Cable should be light and inextensible, massless and inextensible. Bara rahita adennathi. Massless cable should be massless and inextensible. Cable should be massless and inextensible. If the cable is massless and yes, it's true, you can't find massless cables. At least there will be a small mass. Okay, but the assumption is that perfectly to be tension to be equal in every and each place of a string, the string should be a light weighted, zero weighted one with a inextensible manner. Then nothing. Lightweight and inextensible. And not only that, now this cable is passing over a pulley. To remain the tensions both sides, to remain the tension in the both sides equal, the pulley should also have some properties. Pulley should be a frictionless and a massless one. Cable should be inextensible and lightweighted, massless, and pulley also frictionless and weightless. The second point, pulley should be weightless and frictionless, smooth. Pulley should be weightless, massless, whatever, and frictionless or smooth. If these assumptions are met, the tension of a string will not change when it passes over pulley. Okay. Now, I have given you 2 marks for these 4 assumptions. Okay. Then part B. Draw clear free body diagrams showing all the forces acting on man and the lift. Use the given diagrams. Okay, I'm going to teach it now again. I have already taught you this. Okay. Now what happens here? When the man pulls the cable downward, what happens? This F1 is the force acting on the cable downward. So man pulls the cable downward with the force F1. Then what will happen? From Newton's third law, there will be a force acting on man's hand upward. Let's say it's F2. What is F2? F1 is the force acting on the cable by the man. Force acting on the cable by the man. He is pulling it down. And from Newton's third law, cable will pull this man's hand upward, opposite and equal. Okay, what is F2? Force acting on man's hand by the cable. Force acting on man's hand by the cable. Man pulls the cable down. Man pulls. Ayyo, grammar nahi there. Okay, yeah. Man. Okay. So he pulls the cable downward. Okay. So he pulls the cable downward. So from Newton's third law, there will be a force acting on his hand in the upward direction. So this F1 and F2 are equal also. This F1 and F2 are equal as they are Newton's third law companions. Okay, you have to, I have asked that later. Okay, now I'm teaching it again. The man pulls the cable downward with the force F1, and what will happen? Cable will pull man's hand upward with the same equal and opposite directional force by the Newton's third law. So this force that is acting on man's hand is attracting man's hand to the upward direction. What does this tension do? What does this tension do? A tensional force always attracts the connected point towards the string itself. So this F2 is a tension. Man pulls the rope downward. So from Newton's third law, man's hand will be pulled upward by the cable. And you have to know what this tension do. A tensional force attracts the connected point towards itself. So this is playing that role. Okay, so this force F2 is attracting the man's hand upward. A tensional force attracts the connected point, man's hand upward. So this becomes a tensional force. And what happens? The tension spreads. When it's closer to a pulley, it attracts the touch point of the pulley downward like this. Here also, it's same. I have taught these things clearly in my theory class. So I'm now just marking them. And what happens here? In the other side, the connected point, it is attracted towards the string itself, T. So I mark the tension now. So what happens here? Man, I'll explain one time. Man pulls the rope downward and rope will come down, passing the pulley in a clockwise manner, and he will move up from the other side. When man pulls the string down from Newton's third law, his hand will be pulled upward with the equal and opposite force. Tension of a string attracts the connected point towards the string itself. So this play the role of a tension. So this force acting on man's hand upward is a tension. Tension spreads, and this is how we mark tension near the pulleys and in the other corner. Tension attracts the connected point upward, so here the tension is here. Okay, so these are the tension. What else? Man has a weight mg, and this vessel, it also has a weight m naught g. Man has a weight mg, and this vessel has a weight m naught g. And when man is touching the ground, when someone touches the ground, he creates a normal reaction force downward, and from ground there's a normal reaction force acting upon him upward. So there are two normal reaction forces also. So this is the situation. These are the forces. Okay, now I'll come to the question. Now I'm going to mark the forces, the external forces acting on the cage. Okay, in a free force diagram or in a free body diagram, we have to mark the external forces acting on that object. Here, now I am coming to the cage. Cage has its own weight, m naught g, m2g. According to them, it's m2g. Cage has its own weight, m2g. We have to mark that. I'm in the question now. I'm in the subpart B. We have to mark the forces acting on that certain objects. That's what called by a free body diagram. We have to mark the forces acting on that certain object. The vessel has a weight m2g. We have to mark that. When man touches the ground, he creates the normal reaction downward on the ground. That means on the floor of the vessel. Okay, you have to mark that R. And due to this criteria, when man pulls the string downward, there was a force acting on him upward, and it became a tensional force. As it attracts the connected point towards the string, the tension spreads, and here it attracts the connected point towards the string, means upside. So this is also a tension. So it's acting here. You have to mark that too. So these are the forces acting on the vessel. Okay. Now what are the forces? What are the forces acting on the man? What are the forces acting on the man? His weight is active. The gravitational force. He's attracted towards ground by the gravity. It's marked as m1. And when he touches the ground, he creates a normal reaction force downward, and from ground there will be a normal reaction force upward on his leg. It's equal to this. This is marked by R1, the force acting on the cable downward. It's R1, force acting on the man upward, the other normal reaction component. They asked to mark it by R2, but we know they are equal. Man creates a force downward when he touches the ground from his leg. Due to that force, there's a Newton's third law companion bond, and it acts on the man upwards, R2. They are equal. We'll discuss that later. And what else? R2, M1G, and what else? He pulls the string downward. Then from Newton's third law, there's a force acted on his hand upward. That tensional force acting on his hand. T. This one. Okay. So it's also here. So these are the forces. I gave 2 marks to this diagram and 2 marks here. Okay. Part C, identify the action and reaction force pairs acting in the system. Most of you have written this R1 and R2. That's correct. They are they are Newton's third law companions. Force acting on the ground by man's leg and the force acting on man's leg by the ground, R1 and R2. They are Newton's third law companions. That's correct. I gave 1 mark, but there's another mark we have to give. What is the other Newton's third law couple here? Man pulls the string downward here, F1, and string pulls the man's hand upward, F2. That is the force that becomes a tension as it attracts the connected point towards string itself, and that's the force that spreads. Okay, so this F1 and F2 these are Newton's third law companions. So I haven't named them, so you have to write it here. Okay, write the next pair. The force, okay, let's write it in an easier manner. Let's say like this. The force that man pulls the string downward, the force that man pulls the string downward and the force that pulls man's hand upward by the string. So that's also a Newton's third law companion. The force that man pulls the string downward and the force that attracts the man's hand upward here, F1, F2. They are equal and opposite. They are Newton's third law companions. Actually, that is the beginning of this scenario. That's why the movement started. Okay, by the force that man pulls down the string is coming down, so it has to pass the pulley in a clockwise direction. That's why the lift was taken up. Meantime, there was another force acting on man upward. That's true, but man is here, and all these forces were combined and made this final motion. Okay. After that, there's a small mathematical part. There's a small mathematical part. Okay. Then you are asked to find these values. Okay. Part D. If M1 is equal to 100 kilograms, M2 25 kilograms, R1 450 newtons, determine the acceleration of the system. Okay. I am applying F equals ma for the man. I'm applying F equals ma for the man. If I am applying F equals ma for man, what is this F? This F is the resultant force on man. If I applying F equals ma to a certain object, F denotes the resultant force acting on that object. I'm applying F equals ma upward. I'm applying F equals ma upward. So this F denotes the resultant upward force acting on the man. So I'm applying F equals ma for the man. So this F denotes the resultant upward force acting on the man. On man's hand, there's a upward force, a tension T. On man's hand, there's a upward force, the tension that attracts man's hand upward due to his pulling of the string downward. There's a force acting on man's hand upward, that T. It's on man. What are the external forces acting on man? the upward force that attracts man's hand upward from the tension street, T here, this T. And the normal reaction force acting on his leg by the ground, R is also there, T plus R. What are the external forces acting on the man? This T. And here, this R. And his weight is in the opposite direction. So it will become a minus. His weight is downward. So it will become a minus as I am considering the upward resultant force. T on his hand, R on his leg, minus M1G is equal to M1A. I don't know T, but they give R1 as 450 minus his weight, M1D 1000 is equal to 100A. So T 450 minus 1000 minus 550. T minus 550 is equal to 100A. That's my first equation. Okay, T minus 550 is equal to 100A. First equation. And I'm going to apply F equals MA again. Applying F equals MA for the man and the lift. Again, I'm applying F equals MA for the man and the lift. If I apply F equals MA only for man, what are the forces acting upon him in the upward direction? Tension, normal reaction on his leg, and minus the weight as it's in the other side is equal to M100A. And again applying F equals MA on both of them. Now I am applying F equals MA on both man and cage together. Okay. So there's an upward force acting on man's hand. It's a tension T. So there's an upward force acting on man's hand. It's the tension T. Again, from the other side, there's a tension acting upon the roof of the cage upward. It's also a tension. It's also T. So when you consider both of them, there are two T's. One on man's hand, other one is on the roof of the cage. Two T's. And what else? When the man touches the ground, there's a normal reaction force acting upward on him. But you have to consider the cage also. When man touches the ground, there's a normal reaction force acting on the cage downward. It's minus. And weight of the man and weight of the cage, they are minus, is equal to M1 plus M2. Combined weight, M1 plus M2 into A. Combined mass into A. Okay. I'm applying F equals MA for the man and the cage both. On man's hand, there's a tension upward. On the top of the roof of the cage, there's a tension upward, 2 T's. On man's leg, there's a R upward. On ground of the cage, there's a R downward. So plus R and minus R, as I'm considering both. And two weights downward, so they are minus, is equal to the combined weight, combined mass M1 plus M2 into A. Okay, these R's will cancel out. 2T minus M1G minus M2G is equal to M1 plus M2A. 2T minus 1000, weight of the man, and weight of the cage, 250, equal to 125A. The combined mass 125A. Applying the equation for the man and cage both. 2 T's upward, 2 weights downward, R and R, 2 R's are cancelling. Okay, 2T minus 1000 minus 250, 2 weights, R's are already cancelled. The addition of the weights 125 into A. 2T minus 100 and 1250. 2T minus 1250 is equal to 125A. It's the second equation. It's the equation Y. Okay. Now I can solve equation X and Y. Now I can solve equation X and Y in order to find the final answer. I applied F equals MA for man only and then got this equation. T minus 550 is equal to 100A, equation X. Then applied F equals MA for the man and the cage both, the combination. Then what happens? Two r's cancelled, and then I got another equation. 2t minus 1250 is equal to 125a, equation y. So I can solve these simultaneous equations in order to find the things they ask. They ask to find the acceleration. So how to do that? Okay, I'll multiply equation x by 2. I'll multiply equation x by 2. Equation x, t minus 550, 100. If I multiply it by 2, 2t minus 1100 is equal to 200. 2t minus 1100 equal to 200, and what is the equation y? It is 2t minus 1250 is equal to 125a. Okay, then what will happen? No need of doing such things. No need of doing such things. Here the first equation, 2 minus 550 is equal to 100. 2 minus 550 is equal to, actually there should be another thing, no? 2 minus 5, wait, I will check. T, applying F equals MA for man, T minus 1000 equal to MA, 100A. So there's this 100A acceleration. I forgot that term. I'm sorry. I forgot that term. It's 100A. It's 100A. No, we apply F equals MA for man. The force acting upon him, T plus R. T plus R minus 1000. Its weight is equal to 100A. So you have A here. When you're applying F equals MA for man, his weight, mass is 100, acceleration is A. He's also moving upward with the cage. When we apply F equals MA for the man, he is also moving upward with the cage as he is inside the cage. So in right side of the equation, MA 100 into A. You have A there. Okay, now I have to do what I did earlier. Okay, I'll multiply the equation x by 2. 2t minus 1100, 200A. Equation y, I'll write it again. 2t minus 1250, 125A. Okay. Now I'll subtract like this. 2t minus 1100. First equation. I'm subtracting the second one from it. 2t minus 1250. So in the right side, 200A minus 125A, 75A. I have to write the two equations, and one is with a single t, other one is with the 2t. Then I multiplied the equation with t from number 2, the numerical value 2, and get the equation c. Okay, then I'm subtracting the equation y from equation c. C minus y, 2t minus 2t minus 1100 here, subtracting 2t minus 1250 here, 200A minus 125A, 75A. Okay, what will happen? 2t will cancel out, 1100 minus into minus plus 1250 is equal to 75A. Here what will happen? 150 is equal to 75A. Acceleration is equal to 2 meters per square second. I gave 4 marks for the mathematical part. I gave 4 marks for the mathematical part. Okay. I gave 4 marks for the mathematical part. Then part E. Determine the force exerted on the roof that it is hung by the pulley. Okay, there's this string, the cable passing over the pulley, and the pulley is subtended, pulley is attached to the roof. Pulley is attached to the roof. You know, when you are marking the tension in a pulley, when you are marking the tension on a string that passes a pulley, 4 tensions are marked. Here, one tension, here, one tension attracts disconnected point towards the string itself. And when a string is touching the pulley, it attracts the connected point downward. Can you remember that theory? So the touched point of the pulley here, it is attracted downward by the tension. Even though we mark the tension on the string, actually the tension shows us the forces acting on the connected points of the string. So here the force acting on man's hand is the tension. Even though we marked it as a tension on the string, that's true, that's the theory I'm explaining again. The tension is marked on the string, but it indicates the force acting on this connected point. The man's hand is attracted upward. Likewise, when it touches a pulley, the string attracts the touched point of the pulley downward. We mark it on the string, but it is the force acting on the touched point of the pulley, T, downward. And from the other side also, the string attracts the touched point of the pulley downward towards the string itself, T. Theory. So there are 2 T's acting on the pulley downward. So 1 T is equal to, we have to find the value, T minus 550 100A, T minus 550 100A, T minus 550 100A, T minus 550 100 into 2, acceleration is 2, we already found. Okay, so T is equal to 550 plus 200. T is equal to 750 newtons. T is equal to 750 newtons. Okay, so the tension is 750. Tension attracts the connected point towards the string itself, and it attracts the touched point of the pulleys towards the string itself. So the string here the string is in the middle area. The tension attracts the touched point of the pulleys towards the string, to this side, this T, towards the string, this T. The T value is 750. So it attracts the touched point of the pulley towards the string itself, 750. From this side, again it's 750. So the pulley is attracted downwards by a 1500 Newton force. So altogether, from both sides, the addition, the pulley is attracted downward by a 1500 force. To maintain the equilibrium, as the pulley is in the equilibrium, it doesn't move, it doesn't come down. So the force acting on the pulley by the string that it was connected to the roof. This is the string that connects the pulley to the roof. As the pulley is attracted downward by 2 forces, which is the addition equal to 1500, and still the pulley is not coming down, forces should be cancelled. So this is string, the blue string that I have drawn, it will attract the pulley upward with the 1500 force to be cancelled with this one. As this string is also a string, it has the other side tension. So it will attract the roof downward with a 1500 Newton force. So this is the force that I asked you. So this is the force that I asked you. So it's 1550, not 750. It's 1500. There are 2 750 forces acting downwards on the pulley tensions, but still the pulley is stationary. So the string that keeps the pulley hung to the roof should exert a equal value opposite force to keep the pulley in a stationary position. As this addition is 1500 and the pulley is weightless, so you don't have to mark the weight. 1500 downward, so the blue string will create a force upward equal to 1500. That's why the pulley is stationary. From as it's also a tension, as it's also a string, the tension has this opposite side force from the other end, it will attract the roof downward with a 1500 force. For that thing, I gave 2 marks. For that thing, I gave 2 marks. Okay. Then I'll come to the part F. Part F. Okay, now this earlier method is over. Now there's a electric motor, I think, electric or whatever. There's a different method. Should be a motor. This motor will turn the pulley and the lift is moving up with the man. Okay. Part F, Roman number 1. The lift is now made to move using a mechanical system. It should be a motor instead of the man pulling the cable. Roman number 1. If the lift accelerates upward with an acceleration of 5 meters per square second. Due to this electric motor turning in an anti-clockwise direction, this string will be rotated around this motor and this man will move up with the lift with the acceleration of 5 meters per square second. Determine the normal reaction force exerted by the lift on the man. Determine the normal reaction force exerted by the lift on the man. So here, weight of the man is 1000 newtons. Now, to find, now the weight of the man is 1000. I marked it. When someone touches the ground, what happens? He exerts a force downward on the ground, and by the Newton's third law, there's a force acting upward on his legs. R, normal reaction. That's how it's created. We push the ground downward, and there's a normal reaction acting on us upward. To apply F equals ma for the man, we have to consider the external forces acting on him. Newton says in his equation, in his F equals ma equation, F denotes the external resultant force to the certain direction acting on that object. Okay, so I'm selecting the man as the object. So I have to write down the resultant external force acting on him. So as he creates a force downward by his leg, the downward normal reaction on the lift's flow creates an upward normal reaction on him. For Newton's equations, we have to consider that part, that component, the force acting on him, the force acting on that object. Okay, so on him, there's a normal reaction upward. To denote this F, the resultant, there's a normal reaction upward acting on him minus his weight, the gravitational pull. Gravity pulls him down. So what is the resultant force acting on the man in the upward direction? R minus 1000 is equal to 100 A, his mass acceleration. So R minus 1000 is equal to 100 into 5. Acceleration is 5. So R is equal to 1500 when he is moving upward. In the Roman number B, it's the same diagram, but the motion is in the opposite direction. Now the motor is turned in the other side, rotated in the other manner, and this lift moves down with the acceleration of 5 meters per square second. Now it's moving down. The man is standing inside the lift. His weight is already there, 1000 newtons. Even though the lift is moving up or down, it doesn't affect the structure of the forces. It affects that how you use the equation. If the motion is changed, change the direction of the equation, and with respect to that direction, the forces will become plus and minus, they will interchange. But how you mark the forces, that won't change. The weight acts downward on him, 1000, and he pushes the ground downward, and from ground there's a normal reaction created on him upward, R dash now. It won't change. The gravitational call, it's downward, the gravity, and man pushed the ground downward by his legs. It's downward. It's acting on the cage. Don't need to consider that. We are considering the man. So the cage acts a normal reaction force upward on the man. It's R dash now. Applying F equals ma for man in a downward direction. When we are applying F equals ma downward, F should denote the downward resultant force acting on the man. Gravitational call, weight 1000 minus R upward, 1000 minus R dash. In this situation, what is the resultant force acting on the man in the downward direction? As I'm using the equation in that manner. 1000 minus R dash. 1000 minus R dash. He is exerting a force downward on the ground, and the ground creates a force on him in the upward direction. We have to consider the forces acting on the man. As Newton say, 1000 minus R dash in the downward direction will be the resultant force, is equal to 100 A. 1000 minus R dash, 100 into acceleration 5 meters per square second downward. Okay, what will happen? R dash will come to the other side, 1000 minus 500. Now R dash is equal to 500 Newton. So we say what happened? When the motion changes, the normal reaction value has changed. So that's why we are telling this R is a self-adjusting force. In theory, that's why we say this R, the normal reaction, is a self-adjusting force. It changed the value according to the motion. Earlier it had a value of 1005. Now it has a value of 500 as the motion has changed. A self-adjusting force. Okay. So I gave 2 marks for this part and another 2 marks for this part. Okay. Now I have asked you another 2 questions. Part G. There I have to teach you something, I think. Part G. At which instant does the man feel heavier than his actual weight? Now listen to this. Actually, we think that we feel the weight, but this is how it happens. When we are standing on the ground in a stationary manner, what happens? Our weight is downward mg, and there's a normal reaction force acting on us upward. If we are stationary, if we are in an equilibrium state, if we are not moving, what happens? Forces should cancel. So man's weight is downward, and the normal reaction force is upward, and R is equal to mg. Actually, the force that we feel is the normal reaction. Then why we say that we feel the weight? In a stationary case, the normal reaction is equal to the weight. Actually, when we are in the ground, what we actually feel is the normal reaction acting on us. When we are on the ground, there's a normal reaction force acting on us in the upward direction. That is the force that we feel. But if we are stationary, to keep us in a stationary position, vertical forces should cancel out in opposite direction. So the R will have the same value of mg. So we say we feel mg, but that's what happened. We feel R, and it's equal to mg when we are stationary. But when we are in a motion, R will change its value. So when we are in acceleration, when we are in a vertical acceleration, we will not feel the correct weight. We will feel a different value. Write a small star mark. Normal reaction is the normal reaction acting upon us. normal reaction acting upon us, is the force that we feel as weight. Normal reaction acting upon us is the force that we feel as our weight. If we are stationary, normal reaction is equal to our weight, normal reaction's value. If we are stationary, normal reaction's value is equal to our weight. So we can say that we feel the weight correctly. But as R is a self-adjusting force, it will change its value. When we are in a vertical acceleration. Here in the first part, in the first Roman number, R value became 1500 newtons. Here in the first Roman number, R became 1500. So at that situation, we feel heavier than our actual weight. As the weight is equal to 1000 newtons. 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 Okay. When we are standing in don't write, just listen again. When we are standing in a flow, the flow creates a normal reaction upward on our body. That is the feeling that we get from the ground. Actually, we think that is our weight, but this is how it happens. When we are on the floor, there's a normal reaction acting upon us on the upward direction. These are. It is the feeling that we get to our legs, to our feet. Okay? So it's a normal reaction. But if we are stationary, in most cases we are stationary, to be kept stationary, body to be kept in a stationary position, this weight and R are equal. Why? The vertical forces should cancel out to become the object in a equilibrium position. So R and mg are equal from values, even though they are opposite in directions. So we feel R is equal to mg when we are at the equilibrium. Okay, so we can say we feel weight. But if we are in a vertical motion, it's a rare case, but if we are in a vertical acceleration, upward or downward, whatever, If there's acceleration, R will change its value. You saw that. In both cases, upward and downward, in both cases, R was changed. It's a self-adjusting force. So when R is changed, the R is the force that we feel. So our feeling is different. It's not the actual weight. It feels higher in this situation, in this question. R is equal to 1,100 and 1,500 when the lift is moving with the acceleration of 5 meters per square second upward. Okay, so at that moment, we'll feel heavier than our actual weight. In the other case, we will feel less weight than our actual weight in this situation. Okay, that's another question H. There's another question H. What is H? If the man experiences apparent weightlessness, determine the acceleration of the lift at that instance. Okay, so now I already told you, as weight, we feel this normal reaction. Weightlessness means we don't feel weight. Actually, we don't feel weight, we feel R. In the opposite stationary cases, R is equal to mg. That's why we told it as weight, that we feel weight. Okay, so here, if the man feels weightlessness, බර නැති බව, weightlessness, R කියලා, weight එක කියලා feel වෙන්නේ මොකද්ද? Normal reaction එක. What we feel is the normal reaction. So it should become 0. If the man feels the weightlessness as weight, we feel the normal reaction. So it should be a situation where the normal reaction is equal to 0. Normal reaction is equal to 0. Shall I show it to you? Shall I show it to you? හදිසිය lift එක කැඩුනා. If the cable breaks and lift is moving down in an acceleration of gravity value. Cable was broken and now the lift is moving down freely with the acceleration of gravity. Let's apply F equals ma for situation like that. Cable was broken. Let's assume the cable was broken and the cage and the man is coming down freely. Now for this instant, cable is broken and the lift is moving downward in the free fall with the acceleration of gravity. Let's apply F equals ma for that kind of a situation. The weight is mg. The weight is mg. When he touches the ground, there's a normal reaction force acting upon him in the upward direction. Applying F equals ma downward, mg minus r. If he is in a free fall, acceleration is equal to the acceleration of gravity mg. Then what will happen? Mg minus r mg. These mg's will cancel out. 0 is equal to r. R will become 0. So R is the force that we feel as the weight. So we will feel the weightlessness. You have to know that. You have to know that. Okay. Before writing this, write this small star mark. Before writing this, write this small star mark. We feel R as weight. I'll give it in a shortened manner. We feel R as our weight. We feel R as our weight if we are in a free fall. We feel R as our weight if we are in a free fall. If we are in a free fall with A equals G. With A equals G. With A equals G. R will become 0. R will become 0. So no force will be felt on our legs. So no force will be felt on our legs. So no force will be felt on our legs. Even though we are standing, even though we are standing on the floor of the, even though we are standing on the floor of the lift, even though we are standing on the floor of the lift. It is called weightlessness. It is called weightlessness. It is called weightlessness. Draw this. It is called the weightlessness. A-level exam එකේ තුන් පාරකට වඩා මේ පොයින්ට් එක අහලා තියෙනවා. A-level exam එකේ තුන් පාරකට වඩා මේ පොයින්ට් එක අහලා තියෙනවා. විෂයක් හරි පුළුල්. හරි. ඒකට මේ ඔක්කොම ටික කවර් කරගත්තොත් තමයි 100 මාක්ස් අරන් අපි එක්සෑම් එකට යන්නේ. එතකොට තමයි ලකුණු 25ක් කැපුණත් ඒක ඉතුරු වෙන්නේ. භාගෙට ඉගෙනගෙන ගියාම යන්නෙම ලකුණු 75ක් විතර අරගෙන. සුළු කිරීම වලටයි අතුරු එවෙලේ වර්ධනයටයි කැපුණාම කොහොමත් ඒකක් ගන්න බෑ. ලකුණු 100 දැනගෙන යන්න ඕනේ. එවෙලේ වර්ධනයටයි සුළු කිරීම වලටයි කැපිලා එවෙලේ හදිසියට මතක් වෙන්නේ නැති ඔක්කොම අකරතැබ්බ වලට කැපිලා හරි ඒත් 75 බේරෙන්න 100 අරන් යන්න ඕනේ. තේරුණාද? ඒතර මේ පොයින්ට් එක විභාගවල තුන් පාරකට වඩා අහලා තියෙනවා. අවමය තුනක් මගේ මට දැන් මේ මත කෙලින් මතකයට එනවා. පාස් පේපර්ස් වල. තේරුණාද? ඒකට 100 මාක්ස් ගැදර් කරගන්න කලින් දවසේ රැයට බෑ ඔයගොල්ලෝ වගේ. throughout the process හරි ගුරුවරයෙක් එක්ක එකතු වෙලා වැඩ කරන්න ඕනේ. ඒතර එයා දක්ෂ වෙන්න ඕනේ. දැන් ළමයින්ට විෂයන් තුනක් තියෙනවානේ. එයා දක්ෂ වෙන්න ඕනේ throughout the syllabus එකේ තියෙන පුංචි පොයින්ට් එක, ලොකු පොයින්ට් එක, තියරි එක, වැඩි පොයින්ට් එක, අඩු පොයින්ට් එක, කෙලවර තියෙන පොයින්ට් එක ඔක්කොම ළමයට ගැදර් කරලා එයාගේ පේපර්ස් ටිකෙනුයි තියරිටිකල් නෝට් එකෙනුයි එයාගේ වැඩ ටිකෙනුයි ළමයට අරන් දෙන්න. ළමයා දක්ෂ වෙන්න ඕනේ ඒ ටික ග්‍රැබ් කරගන්න. ওই දෙක එකතු වුණොත් ඒකක් එනවා. මොන තේරෙන සිංහලෙන් කිව්වා. හරි. ඒකට ළමයාට තියෙන හැම විෂයන් තුනක්. ඒතර එයාගේ විල් පවර් එකෙන් එයා වැඩ කළොත් ගුරුවරු තුන් දෙනාත් එයාට හරියට එයාලගේ 50% එක කරලා දුන්නොත් 3S ගිය හැකියි. Okay, now I'll explain it once again. We don't feel weight at any situation. What we feel is the normal reaction. The force acting upon us from the ground. That's what we feel when we are on the ground. Now keep your legs on. I know that your legs are on the ground now. You have a feeling. That's the normal reaction acting upon your leg. Now you keep your legs on the ground. There's a feeling. What is that feeling? The normal reaction acting upon your leg by the ground. It's upward. If you are stationary, its value should be equal to mg to be cancelled out, keeping your equilibrium. So we say we feel weight. But if you are in a vertical acceleration, r will not be equal to mg. Okay, so sometimes we might feel heavier than the actual weight or less heavier. If in the Roman number 2, that case, or sometimes we might feel nothing to our legs. Actually, you feel something, but say you are in a lift that is in a free fall. The cable is broken and the lift is in a free fall. It just comes down on the atmosphere with the acceleration of gravity. In a such case, let's apply F equals ma downward to the man. His weight is downward mg. There's a normal reaction force. Let's assume there's a normal reaction force acting on him upward. Normally, there's a normal reaction force acting on man's leg upward. His weight is also there. So we'll apply F equals ma downward for man inside the lift when he's coming down. Mg minus r. Mg minus r is equal to ma. If he is in a free fall, acceleration is equal to acceleration of gravity g. Then what happened? This mg and this mg cancels and r become 0. So if we are in a situation like that, our legs will feel nothing. ඔයා lift එකක යනකොට ඔයාගේ කකුල නිකන් මුකුත් දැනෙන්නේ නැහැ වගේ නම් ඒ කියන්නේ තව ටිකකින් තෑග්ග හම්බ වෙනවා. හරි? ඒත් එහෙම වෙලා නැහැනේ දැනෙනවනේ මොනවා හරි. ඒ කියන්නේ safely lift එක යමින් තියෙන්නේ. Okay? Remember that situation, nah? And at that situation there's a special word in physics, weightlessness. Weightlessness. Okay. Now we have continued the class for 1 hour and 24 minutes. As it's our second day for the paper class. Last week we did a term test practice class. Then from this week we are continuing the paper class until our 2027 A-level exam. So let's consider this is the second day or first day or whatever. Okay. Now today I'm going to wind up from here. Okay. And we have these MCQ questions. For the difficult MCQs, I will provide you an answer sheet. For the difficult MCQs, I will provide you an answer sheet. හදිස්සියට වැඩ වැඩි කරගෙන කලබල කරගෙන යන්න පුළුවන් ගමනක් නෙමෙයි. මොකද යන්න තියෙනවානේ දිග ගමනක්. දවස් බර ගානක ඒ ලෙවල් එනකම්ම consistently යන්න ඕනේ. ඒ නිසා එකපාරට වැඩ වැඩි කරලා හරදර කරන්නේ නැහැ. නමුත් ටික ටික වැඩ අනිවාර්යයෙන්ම වැඩි වෙන්න ඕනේ. හරි? ඒක මම කරන්න. පවන රාජකාරිය ඔයා හරියට කරන්නකෝ. එතකොට ඒ ටික තමයි විස්තර ටික. ඉතින් ඔන්න අදට එතකොට මම මොකද කරන්නේ? මම ටික ටික වැඩ වැඩි කරනවා. හරි දැන් අද 1 hour and 25 minutes discussion එකක් ගියා. ඕකේ. හරි. එතකොට මම group එකට හෙට හවසට නැත්නම් සෙනසුරාදා හවසට මම ඇඩ් කරනවා. ගොඩක් විට සෙනසුරාදා හවසේ මට හෙටත් දවසම class, Saturday දවසම class. මම ඇඩ් කරනවා අර MCQs වල important MCQs වලට written discussion එකක්. ඒතර ඒකෙනුත් දැන් marks ටික මම එවලා ඇති. ඒ ටිකත් බලා ගන්න. බලාගෙන ඒකේ තමාරු වැඩ ටික කරන්න. ඒ අතරේ මොනවා හරි අමාරු තැනක් තිබ්බොත් පන්ති ළමයින්ට ක්ලාස් එකේදී මගෙන් අහගන්න පුළුවන්. ඒ අතරේ එහෙම නැත්නම් WhatsApp message එකක් දාන්න පුළුවන්. ඒතර මම සාමාන්‍යයෙන් කරන්නේ voice message එකක් හරි ළමයින්ට එවනවා. හරි. මෙහෙම හදා ගන්න කියලා. ඉතින් ඔය වගේ හොඳ combination එකක වැඩ යන්න ඕන. හරි. හරි. මම ඒතර written discussion එක Saturday evening, Saturday night දාලා තියන්නම්. හරි. එහෙනම් වැඩ ටික හොඳට කරගන්න. වැඩ ටික හොඳට කරගන්න. හෙට උදේ ඉඳලා හෙට උදේ ඉන්ස්ටිටියුට් එක ඇරලා ලොකු ළමයින්ගේ පන්තියකට එතකොට 7:30 ඉඳලා 5:30 වෙනකල් පේපර් එක ලියන්න පුළුවන්. එතකොට ඊවිනිං ටයිම් එකේ ආවොත් මේ පේපර් එක ලියන්න පුළුවන් මේ AC ෆැසිලිටි එකත් එක්කම. ඒ කියන්නේ ඊවිනිං ටයිම් එකේ එතකොට අපේ එළියේ පේපර් එක ලියන්න නැතුව ඇතුලේ AC ෆැසිලිටි එකේම පේපර් එක ලියන්න පුළුවන්. නැත්නම් අර එළියේ අපිට අපි පේපර් සාමාන්‍යයෙන් ක්ලාස් එකක් ඇතුලේ යන වෙලාවට ලියන තැන පේපර් එක ලියන්න පුළුවන් මේ උදේ ඉඳලම ආයතනය ඇරලා. ඔය ටික තමයි එහෙනම් good night. හරි. මම එවන්න ඩිස්කෂන් එක Saturday evening. හරි.